All right. For problems 1 through 3, use the coordinates to find the values of all 6 trigonometric functions. I'd say, especially on the test, when in doubt, draw a coordinate plane, especially if it's giving you some information about the trigonometric functions. So when we're looking at this one here, cosecant of x is equal to negative 7, 6, and tangent is greater than 0. So we're needing to find sine of x, cosine of x, tangent of x. We have cosecant of x. We'll need to find secant of x and cotangent of x. So cosecant's negative 7, 6. Well, sine is 1 over cosecant. So it's negative 6 over 7. Now if I draw out a coordinate plane, like this here. So we're told that tangent of x is greater than 0. So tangent is positive. And the only way that sine can be negative and tangent be positive is if whatever this value of x is in the fourth quadrant. Because tangent is positive in the first, not fourth, sorry, first and third. We're in the third quadrant is where tangent's positive in the first and third. Sine is negative in the third and fourth, so we have to be down here. Now that also tells us that cosine and secant are both going to be negative as well. Now we can fill in the information that we have. So cosecant, or well, sine's negative 6/7, opposite over the hypotenuse. Hypotenuse for the triangle will never be negative, which means our y value is going to be the negative value. Now at this point here, we can use Pythagorean's theorem. Negative 6 squared plus b squared is equal to 7 squared. In all likelihood, this is going to give us a number that will not reduce, so we're going to end up with a square root, because b squared is equal to 13, square root both sides, telling us b is plus or minus the square root of 13. And because we're on the negative x-axis, this would be negative. Questions on this so far? Now to find the rest of it, cosine adjacent square root of 13 over the hypotenuse, which is 7. Tangent is opposite over adjacent. Well, that'd be negative 6 over negative square root of 13. We could go through the process of rationalizing the denominator, or we can just plug it in the calculator. Giving us this here. Now we do need to find the other two. Well, secant's going to be 1 over cosine. So 7 over negative 13th, square root of 13, over negative second square root 13, negative 7 square root of 13 over 13. And lastly, cotangent. Well, we could flip our 6 square root of 13 over 13, or we can just flip our 6 over the square root of 13, which actually just gives us the square root of 13 over 6. Either way, if we did flip the 6 square root of 13 over 13, it would have been 13 over 6 square root of 13. We could plug it into the calculator, and it would just tell us it's the square root of 13 over 6. In either one of these cases here, when we get the radical in the denominator, the bottom of the fraction, and you know it's going to be there, if you don't want to write it out originally, you just want to plug it into the calculator, let it rationalize it for you, that is perfectly fine. You don't have to write down -6 over negative square root of 13, then simplify it. You can go on and simplify it. Well, we can also know that the negative and negative for tangent would have been positive, and we could have gone from there. Questions on 1 or 2? Question on 3. So those are the same. If you do have questions, we can come back over them. 4 through 7, factor each expression. Which one do we want to look at first? Number 4. Cosine of x minus 2 over cosine squared of x minus 4. Well, the numerator is as simplified as it gets. And I know it's not as simplified as it gets because cosine is to the first power, and there are no like terms between cosine and 2. Now the denominator, cosine squared of x minus 4, is factorable. And it's actually a difference of perfect squares. That means we'll have plus and minus. And the reason we know it's a difference of perfect squares is, well, cosine squared is cosine times cosine. And 4 is 2 and 2. Questions on this here? Now at this point here, we do have something in common on top and bottom, cosine of x minus 2, which will simplify out, leaving us with 1 over cosine of x plus 2. And that's it. It's not asking us to go any further than this because, well, we'd have to do a lot more to make it simpler than this here. Questions on this here? Questions on number 5. Secant to the 4th minus tangent to the 4th. This is a difference of perfect squares. I'm going to say u is secant squared of x, and I'm going to say v is tangent squared of x. Because here, secant to the 4th, well, we can say that's the same as secant squared of x squared minus tangent squared of x squared. Because when we put a power to a power, they multiply, which would give us secant to the 4th minus tangent to the 4th. And using our uv substitution, really we're saying that we have u squared minus v squared, which is another difference of perfect squares. So the signs are opposite. Then we'd have u and u and v and v. Questions on this here? Now, we'll go on and replace what we have. So this would be secant squared of x plus tangent squared of x times secant squared of x minus tangent squared of x. Now this here, secant squared plus tangent squared is as factored as it gets. Because we don't have a sum of perfect squares. We have a sum of perfect cubes, but not a sum of perfect squares. However, if we look at the second set of parentheses, the second one, secant squared of x minus tangent squared of x, is a difference of perfect squares, which will factor to secant squared of x plus tangent squared of x times secant squared of x minus, not squared. I don't know why I'm putting squared. Because it just should be secant tangent of x. Because when we do the difference of perfect squares on secant squared minus tangent squared, it should be secant plus tangent times secant minus tangent, telling us that the completely factored form of secant to the fourth minus tangent to the fourth is secant squared of x plus tangent squared of x times secant of x plus tangent of x times secant of x minus tangent of x. Questions on this here? Questions on 6 or 7? 7 is actually factoring by grouping, because we'll group them together. And normally with 4, I group the first two and then I group the second two. So if we look at secant cubed minus secant squared, what's in common with both those terms? Secant of x, how many of them? So there's 3 here and 2 here, so they have it in common, 2. So if I take 2 of them away from secant cubed, we're just left with secant of x minus. So I'm going to run out of space. Scoot that over a little bit. Now secant squared out of secant squared would be 1. So we can factor a secant squared out of both of those, giving us secant minus 1. Now for grouping, factoring by grouping to work, we need what's in this other set of parentheses to also be secant of x minus 1. Because if they're both the same, then we can factor it out and it'll be completely factored. However, our secant that we have right now, secant of x is negative, not positive. And our 1 is positive, not negative. So what we can factor out is a negative 1. Because if I factor a negative 1 out of negative secant of x, it becomes positive. If I factor a negative 1 out of positive 1, it becomes negative. Now we do have 2 like terms. So we can factor a secant of x minus 1 out of both, giving us secant of x minus 1 times secant squared of x minus 1. Questions on how we got to this here? Funny enough, this actually still factors. Secant squared is a perfect square. Secant times secant. 1's a perfect square. 1 times 1. So again, we have a difference of perfect squares. So that whole thing factors to secant of x minus 1 times secant of x plus 1 times secant of x minus 1. Or if we wanted to write it a little bit simpler, we could have said secant of x plus 1 times secant of x minus 1 squared, because there's 2 of them. Questions on either one of our factoring? Are we ready for the next one? Simplify each expression. Which one do we want to look at first? Number 9. cotangent of u times sine of u plus tangent of u cosine of u. So we want to simplify this as far as possible. Now, we do have tangent, cotangent, sine, cosine. Well, cotangent, in terms of sine and cosine, is cosine of u over sine of u times sine of u. Tangent of u is sine of u over cosine of u times cosine of u. Questions on this here? Yep. Questions on 8 or 10? Yeah, because luckily with 10, we can look back at it later, but the first thing I would do is replace cosine squared of y with its Pythagorean identity, 1 minus sine squared, and then factor. Perform the operations and simplify. Questions on 11 and 12. Or is there one of these two that you all want to see work? 12. So the operation that it's wanting us to apply is the distributive property we're wanting to multiply through. So 2 secant of x times 2 secant of x is 4 secant squared of x. 2 secant of x times 2 is plus 4 secant of x. Negative 2 times secant of x is negative 4 secant of x, and negative 2 times 2 is negative 4. Now if we combine like terms, 4 secant of x minus 4 secant of x is 0. Leaving us with this here. Now if we want to simplify, we can, and it looks like I did on the answer sheet, because this is the product. Now if we factor a 4 out, what we're left with is secant squared of x minus 1. And according to our Pythagorean identities, this is just tangent squared of x. Either one works. They're both simplified. I did put the 4 tangent squared of x on the answer sheet, but really both of them do work. Who knows how that's going to come out. Questions on this here? Questions on number 11. Questions on 13 or 14. 14. Now, for us to be able to add or subtract two rational expressions, we need the denominators to be the same. So, the one on the left, we're going to multiply top and bottom by 1 minus sine of x. The one on the left, we're going to multiply it by 1 plus sine of x. Now, the denominators for both of these are going to be 1 minus sine of x times 1 plus sine of x. We'll leave them as this here, and if it turns out we do need to multiply them through, it's not too big of a deal to do that. The numerators distribute cosine. Cosine times 1 is going to be cosine of x. Cosine times negative sine is negative sine of x. Cosine of x. We could have written those in any order. Our others, cosine of x times 1 is cosine of x. Cosine of x times positive sine of x is plus sine of x cosine of x. Now we can subtract. Our first one's still going to say cosine of x minus sine of x cosine of x. But since we're subtracting everything in the second numerator, both of them are going to become negative. So we'd have minus cosine of x minus sine of x cosine of x. Now the numerator itself will simplify significantly. Cosine of x minus cosine of x is 0. Negative sine of x cosine of x minus sine of x cosine of x would be negative 2 sine of x cosine of x. If we really want to simplify this, we can actually take it one step further. So we'll actually need to multiply this out in the denominator, so we can actually be left with something that's not a fraction. If we distribute this 1 times, well, our 1 times 1 would be 1. 1 times sine of x is plus sine of x. Negative 1 times sine of x is negative sine of x. And negative sine of x times sine of x is negative sine squared. Now the reason I say we can actually simplify this is because these cancel, giving us 1 minus sine squared of x. Now it doesn't directly cross out or cancel, but according to the Pythagorean identity, one minus sine squared of x is the same as cosine squared of x. Well, here, the cosine of x on top will simplify with one of the ones on bottom, telling us that we have negative 2 sine of x over cosine of x. Well, sine over cosine is tangent. And that's it. So some of them, I think for most of our rational expressions, I would leave the denominator as is. I wouldn't multiply through. But I think for the most part with trigonometric functions, it's probably easier to just do the multiplication and go from there, because it seems most of the time with those squares we end up pulling it back out. Questions on 14? Questions on 13? Questions on 15? Okay. Well, again, for us to be able to add or subtract fractions, we need the denominators to be the same. Since only one of them has a fraction, our tangent of x in the denominator, we just need to multiply the first one by tangent of x over tangent of x. Which is going to give us tangent squared of x over tangent of x. Now we can go on and subtract these two, telling us tangent squared of x minus secant squared of x over tangent of x. And as we can see here, did not get simpler. So we're going to use one of our Pythagorean identities. Now, one of the Pythagorean identities is that tangent squared plus 1 is equal to secant squared. So we can do this in either way. We can either replace tangent with secant squared minus 1, or we can replace secant with tangent squared plus 1. I'm going to do the latter. I'm just going to replace secant with tangent squared plus 1. And now we can simplify. Because if we distribute that negative, we get this here. Tangent squared of x minus tangent squared of x is 0, giving us negative 1 over tangent of x. And tangent is the reciprocal of what? Cotangent. So it just simplifies cotangent of x. Questions on this here? Question on anything we've done so far? Rewrite each expression so that it's not in fractional form. Do we want to look at 15, 16, or 17? 16. So to get it not in fractional form, what we're going to do is multiply this by something that's going to make it, well, normally we can do it in different ways. One, we can multiply, or we can try to simplify as is. Now, the reason I kind of backed off multiply is because the numerator is cosine squared. Well, according to the Pythagorean identities, cosine squared of x is equal to 1 minus sine squared of x. And our 1 minus sine squared of x is a difference of perfect squares. So we will have opposite signs. Since 1 came first, its factors 1 and 1 will go first. Sine squared is sine times sine. So 1 minus sine squared factors to 1 plus sine times 1 minus sine. And we get this here. Questions on how we got to this point here? Now we do have something in common on top and bottom. These will cancel, telling us that we have 1 plus sine of x. Questions on this here? Questions on number 17? Number 17, we'd have to multiply top and bottom by cotangent of x minus cosecant of x, because we need to use the difference of perfect squares. Questions on 18 or 19? So again, we want to rewrite this here. And we're going to replace x with the value it gave us. So it told us x was 2 cosine of x. So in our square root is 16 minus 4x squared. We're going to replace the x with 2 cosine of x. I should have chosen some other variable other than x twice. But there you have it. Now at this point here, we do need to do some simplifying. Because our 2 cosine of x squared, 2 squared is 4, and cosine of x squared is just cosine squared. Since there's only one term, we can just square both terms. And that's not supposed to be a 4. It's supposed to be a 1. Because if we do our 4 times 4 cosine squared of x, so our 4 times, well, negative 4 times 4 cosine of x is going to be negative 16 cosine of x squared. Now to simplify it, we will factor the 16 out of both terms, giving us 16 times 1 minus cosine squared of x. We'll still have the 16, but our 1 minus cosine squared of x can be replaced with sine squared of x, because this whole process is just to simplify this radical, if possible. Now the square root of 16 is square root of sine squared is sine of x. So it simplifies to 4 sine of x. Any questions on this here? Get ready for the next ones. Do we want to look at 20 or 21? 21. Write the algebraic expression as a trig function. Okay. So what we're going to do is replace x. We're going to plug 5 sine of x or 5 sine of theta into this here. So we have 5 square root of 3 is equal to the square root of 100 minus 5 sine of theta squared. Okay. 5 square root of 3 is equal to 100 minus, here we can square both terms, which would be 25 sine squared of theta. Unfortunately, we can't simplify this. I mean, we can, but it'd be a little hard to try to simplify it out. But since we do have an equal sign, one thing we can do is square both sides. On the right-hand side, the square root and square would cancel, leaving us with 100 minus 25 sine squared of theta. On the other side, 5 squared of 3 squared is 75. Now at this point here, we're going to try to get sine squared by itself. So I'm going to minus 100 from both sides, telling us that negative negative 25 is equal to negative 25 sine squared of theta. At this point here, we can divide both sides by negative 25, telling us sine squared of theta is equal to, plus minus, I'm getting ahead of myself, 1. Lastly, if we're solving this here, we can square root both sides, telling us sine of theta is equal to plus or minus 1. Yeah. Okay. And we get this here. So this is an algebraic expression if we did want to find theta as positive or negative 1. It would have been pi over 2 or 3 pi over 2 or any variation of them. But it didn't ask us to solve. So we'll leave it as this here. Questions on this? We ready for the next one? Solve each on the interval of 0 to 2 pi. Do we want to look at 22 or 23? 22. Tangent of x plus the square root of 3 equals 0. Well, since tangent of x is only the trig function that we have, we can subtract square root of 3 from both sides, telling us that tangent of x is equal to negative square root of 3. Now between 0 and 2 pi, there's only 2 locations where tangent can have this value. They're in the second and third quadrants. Now, if we wanted to, we can look at the unit circle. And for this to work, we're looking at 60 degrees. Well, the back table tells us tangent of x equals square root 3 at 60 degrees, or pi over 3. So we're looking at, in terms of radians, we're looking at our pi over 3s. So the pi over 3, or over 3 in the second quadrant would be our 2 pi over 3. And our over 3 in the fourth quadrant is 5 pi over 3. And those would be our two values. Now, if we wanted to check this, we can grab the calculator and say tangent, making sure it's in radians, of 2 pi over 3. It'll tell us it's negative square root of 3. Tangent of 5 pi over 3 is also negative square root of 3. So those are our answers. And we're going to